Hey, good day everyone. We're going to talk about the Bootstrap right now. Kind of excited about this. We throw Bootstrap in right now. It's not really related only to bivariate statistics. You could perform the Bootstrap on anything because the Bootstrap is a statistical resampling procedure to calculate uncertainty in a statistic from the data itself. That's why we call it Bootstrap, because it's like that old English saying of pulling yourself up by your bootstraps. You're getting the uncertainty in a sample statistic from the sample itself, which is pretty powerful. So what I'll do is I will show you a workflow for Bootstrap. Then I will get out my cowboy hat and we'll do a really quick kind of just start doing a little bit of Bootstrap with hat in hand. And so let's go ahead and just start talking about the workflow. So imagine you have some type of phenomenon. You have the subsurface, you have porosity, you have permeability, whatever it is, TOC, it doesn't matter. You have something that you're sampling. So in this case, we're sampling EUR, and we're sampling it by drilling multiple wells. And so EUR in subsurface petroleum speak is the estimated ultimate recovery of a well. It'd be measured in the total amount of barrels that you would expect to recover from the well. Okay, so now you have that distribution, which comes from n equals 10 samples, which were the 10 wells you drilled. And so I just sketched a distribution. Please don't look at it too carefully. I'm sure it's not perfectly correct, but I made what should be a histogram of the outcomes from the 10 wells. We can convert that into a CDF, and now we have a CDF. It's not a big deal. We can just integrate across CDF from a histogram or from a PDF. It's pretty straightforward, integration. Okay. Then what we do, once we have the CDF, we're going to take and do 10 Monte Carlo simulations, 10, because n was equal to 10. So we're going to draw 10 times with replacement from that distribution, which is effectively the same as doing 10 Monte Carlo simulations directly from that distribution. So I do the 10 Monte Carlo simulations. They're all independent of each other. There's no correlation or anything here. I do 10 simulations. Every time I do a simulation, I get a value. I do 10 times, I get a new distribution. Would you agree with me that that distribution will not be the same as the original distribution that we used to build that CDF? There is the possibility it's going to be different. And so we'd expect it to be different. If you had 1 million samples and you were doing 1 million resamples or Monte Carlo simulations, maybe in that case you'll get back exactly what you put in. But if for the case of 10, you could imagine that you could have this one sample here drawn 2 times. Or maybe this one sample responsible for that little piece of bar there could be not drawn at all. And so the histogram will change based on what happened with those 10 Monte Carlo simulations. We get a new histogram, and you calculate the statistic you're interested in getting uncertainty in. In this case, it's just the average of the EUR over 10 wells. Then we put that measure here, and we're starting to build a new histogram right there. Okay, so now we can step forward, and we will repeat. We'll do 10 Monte Carlo simulations from that CDF. We're drawing with replacement from the sample set effectively. We get a new distribution. It's not the same as this one, not the same as the original one. And we calculate the average, and we put the average right here. We repeat that the third time, and so we'll call these realizations. Each one of the realizations comes from 10 Monte Carlo simulations from that initial distribution, and we calculate the statistic of interest, the one that we want the uncertainty in, from that new realization of the distribution, and we plot it right there. You see where this is going. I guess I can spoil it now, right? Basically, you do that L times, where L is the total number of realizations, and L can in fact be a large number. Remember, this computational activity of calculating the 10 Monte Carlo drawings and calculating the average of them is incredibly fast. So you just said L is large. Large enough that we now can define this distribution right here, which is the distribution of the realization averages over all of those sets or L realizations that we have, right? So L realization averages. So we have a distribution. So that distribution will have like 100 or 1,000 samples in it. There will be a distribution. And what's very interesting is that that distribution is now treated as the uncertainty in the average, given the fact that we had this initial CDF and we had 10 samples in that initial CDF. And so that's the Bootstrap idea. You get uncertainty in the statistic from the sample set itself. We took the sample set, built a CDF, we performed N Monte Carlo simulations to get a single realization of the sample set. Then we calculate the sample statistic we're interested in, and we repeat it L times in order to get a distribution of that sample statistic, and that is our uncertainty in the sample statistic. So we get a distribution. So if it's uncertainty in the average EUR, we can now look at the mean. We would expect the mean, there's no bias in the system, we'd expect the mean to be equal to the original sample mean if we have enough L. We did enough samples from it. We would get a variance or a standard deviation, a measure of spread. Now, spoiler alert, the spread will actually be exactly what we would have calculated for standard error of a mean. And we've talked about standard error before, and so it's good. We know that this technique works, it matches what theory should do. Why don't we just use standard error? Well, you can bootstrap anything. I can bootstrap to get uncertainty in the average, the variance, the P10, the P13, my personal favorite percentile, or anything that you want to bootstrap. So extremely powerful. We wouldn't have theoretical methodologies to get at those, but we can bootstrap it. So the Bootstrap approach, it was proposed Ephron back in 1982. This is the general workflow that we talked about before. We're going to gather the sample set. Of course, and my students asked about this in class, I really appreciate that, was the issue around what if you have bias in the original sample set? And the answer is bias in, bias out. If you have bias in the original sample set, that bias will propagate through the Bootstrap. It won't fix it. There's no fixing it through Bootstrap. We'd have to do something prior to the Bootstrap exercise. Okay, so we got N samples. We do N random samples with replacement, so we're going to randomly sample with replacement. I keep saying with replacement because if you didn't do with replacement, every time I drew a sample, I just kept it. If I do N times, you get the same as the sample data set. You're going to sample every sample. So you have to replace them so that you get realizations. You calculate the summary statistic of that realization, L, where we have L through 1, L equal 1 through L, big L, realizations. And then you go ahead and you pool the realizations, the sample statistic from all of those big L realizations, and you can summarize the uncertainty. And we've talked about a lot about different types of summaries of distributions. You can, of course, do a range, max minus the min, interquartile range, P20, P75 minus the P25. You could do a standard deviation. You could do anything. Okay. The power of this methodology is that you can get uncertainty. Any sample statistic, with any sample, with any shape, it's completely general, and we would not be able to do that without Bootstrap. So it's very powerful. Now when you're in a meeting and somebody says, oh, we're going to Bootstrap to it, you now know what we're talking about. You know exactly what that is. It's there's of course advanced forms of Bootstrap that account for spatial context, that count for data collection and so forth. All of these methodologies are much more advanced outside the scope of anything we're talking about here. Okay, let's see what else. It's a super powerful tool. The caveats, just I mentioned some of these, it assumes the sample set is representative. If there's bias in, bias will get propagated through. It assumes all samples are independent, doesn't consider any spatial context whatsoever. They're IID. Independent, identically distributed samples. If you have a spatial context, you have locations with different kind of central tendencies, like a trend model. If you have spatial correlation between samples, now we're using Journell, Andre Journell, Professor Journell, previously of Stanford, the Scurf Center. His concept of spatial bootstrap is what we need to do. And you can do it in Excel. But if you can do it in Excel, you can also do it in a cowboy hat. And so this is my cowboy hat. And what I'm going to do is I'm going to take my hat, I'm going to put it down on my desk right here. And I'll change my view a little bit so you can see my hat right here, my messy desk. And I'm going to take these stickers and put them in the hat. 2 of them are orange stickers for my center. 3 of them are white stickers. And so what's the statistic of interest for me? My statistic of interest is the proportion of orange stickers, because it's burnt orange and I'm here at UT and we got to be kind of liking that burnt orange, right? So basically what I'm going to do is I want uncertainty in the fraction or proportion of orange stickers. So I'm not looking, see I'm looking this way. I'm going to draw randomly in the hat. And so I do a Monte Carlo simulation and my first one is white. I have to take that and put that back with replacement. So it's back in the hat. I'm not looking. I go ahead and draw another one. It's white again. 2 whites. I better keep track of this so I don't get confused. Okay, so white and burnt orange. Okay, so I've got 2. Go back in here and I'm not cheating and I get, I got an orange one. So that's good. So I got an orange one. And in my hat, is this truly a random process? Okay, did I peek? I peeked. Okay. What did I get? I got orange again. And let me see, mix them up, and I drew out an orange one again. Okay, so what did I get? I got, for my first sample set, I got 3 white and, 2 white and 3 orange. So I was worried about the proportion of orange, and so my first realization is 60%. 3 out of 5 were orange. Now remind ourselves that the data set we're working with is in fact 40% white, and that makes 40% orange, and that makes sense that there's no reason to suspect the law of small numbers. In other words, we don't expect every sample set to be exactly the same as far as statistics. Okay, so I could do this again. It would be very time consuming for me to keep doing this, but I could convince you that we could have an outcome for which I could be very lucky and I could get 80% orange. I could just happen to draw 80% orange. I could also be unlucky and draw 20% orange. And who knows, it is possible. We could work it out using the binomial distribution. We could have the case where we get 0%. 0% orange, and we could also have the case where we just happen to draw 100% orange. If I do that enough, what will happen over time is that I will in fact build up a distribution of outcomes, and there would be, I would suspect that since I have in fact 2 orange and 3 white, I would expect this would be centered somewhere around 40%. And I would expect there'd be some spread where I could go all the way down to 0, all the way up, and not necessarily exactly Gaussian distributed, and it would be a discrete distribution. I'd only have cases of 0%, 20%, 40%, 60%, 80%, so forth. But this would be a distribution of the possible outcomes for the proportion of orange, and that would be my uncertainty distribution of orange. And what's really cool is I did all that by simply resampling with replacement from my initial sample set and by having a very good cowboy hat. Okay, I'm kidding. But anyway, I was able to test that out. Now, of course, that's, having a cowboy hat or any type of hat, I'm not specific to hat type, and doing this type of redrawing is a good way academically to explain the methodology, but we can, of course, do it more numerically. Monte Carlo is cheap. We can do it all around us. And so what I've done is I have a Bootstrap demonstration coded up in Excel. I've done it in R too. I think there's something in Python on GitHub, which I've done. And other people have done it too. I'm not, so I got a little bit tricky with Excel functions. So what I have is I have data values 1 through 20, You could adjust the sheet and put more data in here. So I assume I have 20 data values. I draw a random p-value, and I do the norm inverse to get a standard normal value, basically Monte Carlo simulation standard normal values right here. So this right here is my data set. Then what I do is I use the VLOOKUP command to look up the right index, and I use a random times the number of samples truncated by integer plus 1 to get a random value between 1 and 20. 1 and the number of samples. And then I use VLOOKUP to look up by this index and get me one of those random numbers. So effectively this command is just drawing a random value from this set of numbers. And to prove it to you, you can see that negative 1.938 is right here. It's the 8th number. And if you look through, all of these numbers in fact come from this list of numbers right here. And if you look carefully, maybe there's some repeating going on. Can I find something really quickly? No. But there should be some. Oh, here's a repeat right here. You see that? There's a repeat. 2 times that same number was looked up. And it's only 2 times. But you'll find out. So it's with replacement. We just proved it to ourselves. Drawing from these numbers, you can find that number is actually right here. So it's number 11, indexed 11 from that number set. So by doing a little bit of kind of, what's the term for it? Just making it work with Excel, I was able to draw 20 times from this set of numbers with replacement, and that's my realization number 1 right there. Then I did that for L realizations, and so these L realizations would go all the way to 50 realizations. And so this is 50 realizations of those 20 data sets, Monte Carloed 20 times to form new realizations of the sample set. Then what I did is I calculate the mean, the standard deviation, the min, the max, the P10, P50, P90 for each one of those realizations. And then you come down here and I've actually calculated the summary statistics of each one of those summary statistics realizations. Kind of cool, right? And so this here is for the case of 20 random standard normal values, the uncertainty distribution in the min, the P10, sorry, the mean, the P90, and the max. And I got a little fancy. I turned them in the box and whisker. I put outliers. I just made them look good. But what's really cool is that this spreadsheet is showing you the Bootstrap in action by resampling. It's very straightforward. You can get the uncertainty in any one of those statistics. You could add your own statistics in. You could even do kurtosis, skew, anything you like, the P13. And so this is available on GitHub. It's a Bootstrap demo. It's within my repository with Excel numerical demos. A lot of kind of nice intuitive demos in order to test out statistical concepts and just do it in Excel very simply. So just to get a little bit more understanding from what we just did, I'll give you a couple of questions and get you to work on them and then show you the solution. So from this demo, show that the Bootstrap result for uncertainty in the mean is close enough or equivalent to standard error. What is the uncertainty in the P16 used for Dijkstra-Parsons calculation? So add a statistic in and try to calculate its uncertainty from the L realizations. Compare the uncertainty in the mean for the case of 20 samples and 10 samples. What happens to the uncertainty in mean as you cut the number of samples in half? I'll show you the answer in 3, 2, and 1. So what do we have here as far as the Bootstrap result for the uncertainty in the mean being equivalent to the standard error? We can take one example of where we look at the sample standard deviation, 0.87. Number of samples is 20. So sample standard deviation divided by square root of n, we would predict a standard deviation of the mean or to be about 0.19. That should be the uncertainty in the mean. The Bootstrap result was really close. It was about 0.20 from the resampling approach. So that works. You can show that to yourself. Hit enter, recalc, and you'll find that things will jump around a bit because of the fact, once again, that we have only an L equals to 50. If you had L equals to 1,000, it would converge exactly down to standard error. What's the uncertainty in the P16? All you have to do is add a P16 calculation to the summary statistics and then go ahead and summarize the P10 and the P90 of that. Note, each one of those P16s will require some interpolation because you only have 20 samples to draw from, so it's not going to be completely precise, but it still works pretty well. Compare the uncertainty in the mean for the case of 20 samples and 10 samples, what happens. And so what you can see in general is that when we take n from 20 to 10, we go up to a standard deviation in the mean of 0.27. It's about a 40% increase, or 1.4 multiplier on the actual original value. That's what we get. And of course you could go ahead and substitute 1/2 n in the square root, and you could see immediately that gives you a 1.4 something multiplier. Then if we do it by Bootstrap, we'll find we get an answer pretty close to it, and we can prove to ourselves that the Bootstrap method works and that it's matching the theory from standard error. Okay. So here's another Bootstrap example right here, or just an example of a workflow. And so you could be dealing with a subsurface asset where you want to know the uncertainty and porosity for unit B. You've got 12 wells that penetrate unit B. You're going to assume that all of those 12 wells are unbiased and that each one of them is independent of each other. Therefore, you can go ahead and use them in the Bootstrap approach. You can go ahead and you're trying to calculate the uncertainty in the average of the 12. So you would formulate a CDF if they're all equally weighted. That's very straightforward. You do 12 resamples with replacement. You calculate the average. You repeat this step 1,000 times, 10,000 times. It doesn't matter. It's very quick. Just get a nice stable result. Calculate the P10 and the P90 of those realizations, 1,000 or so realizations of the average. And then you could go ahead and use that. Now, that's now your uncertainty in the average porosity. If you want to do a Monte Carlo exercise, as we've discussed before, for uncertainty in oil in place, you could go ahead and use you could fit that distribution, or you could use it as a non-parametric distribution, and do Monte Carlo simulation from it in order to propagate its uncertainty through to oil in place or whatever you want to work with. So this Bootstrap approach is very valuable for getting uncertainty in a sample statistic, and you can propagate it through all of your workflows. I hope this Bootstrap discussion has been helpful to you. Once again, Bootstrap, statistical resampling procedure to calculate uncertainty in a statistic from the sample itself. You get the uncertainty in the sample statistic from the sample. Bootstrap. We're pulling ourselves up from our bootstraps. Okay, I hope that was helpful to you. As always, I'm always happy to discuss. If you have questions, my material's all online. I'll be getting these lecture notes on GitHub too. The examples are also on GitHub, and so I hope this is helpful to you. All right, thank you.